Mr. Redby, this is Viktor Zelentsov of Bauman again. So we just talked to Victoria Mayorova, and we decided to proceed on the existing program. That means that your lecture will be in 3 hours.
And how many? 3 hours? 3 hours?
Yeah, it's 7 p.m. Moscow time.
Be at 7 o'clock your time. 7 o'clock Moscow time.
Yeah, 7 o'clock Moscow time.
11 o'clock here.
Mm-hmm.
Very good.
Thank you. Раз. Мы встряхнем как-нибудь. Уважаемые участники, прошу присаживаться. Dear participants, be seated, please. We are about to start the lecture. Well, as you could see from the agenda, the next point is the lecture, which is called From Gagarin to ISS, Human Spaceflight History. And yours truly is myself, Viktor Zelentsov. I work as an associate professor with Bauman Moscow State Technical University Robotics and Mechatronics Department, and I also work as a science consultant with the Youth Space Center, and besides of that, I had a fairly long career as an interpreter, which I mostly am at this workshop, and I also had some photography jobs. So in particular, if you browse the web, you could see some of my photos of the final launch preparations of Soyuz Cruise and Baikonur. So, speaking of the subject, I would like to start with our current state. So, how many people have been to space? There are various ideas about that because, for example, there are three major concepts to believe that the person has been to space. I will start with the simplest one, which belongs to the United States Air Force, which believes that everyone who went higher than 80 kilometers can be considered as a person being in space. There is another criteria which is more widespread and which is believed to be like commonly accepted, is that FAI, International Aeronautics Federation concept, which says that anyone who flies over that Kármán line, which is 100 kilometers, which is believed to be a border between the atmosphere and space, can be considered space flown. And this is the major criteria used now to assess whether the person has been to space. However, there is a third one, and I would say that's kind of interesting one, and that's the most strict one. That's the criteria of International Association of Space Explorers. And that organization unites flown cosmonauts, astronauts, taikonauts. And that organization believes that you can be a member of Association of Space Explorers only if you have closed one orbit around the Earth, which is probably the most strict and most fair approach because for any kind of serious applications, we need to go orbital. So speaking of that criteria, we can say that 602 people flew orbital missions and 638 people were above 100 kilometers. The growth of that number has been observed over recent couple of years with Blue Origin, New Shepard flying, and Virgin Galactic's flying their suborbital plane. And these are mostly the tourists, but the crew members of those vehicles flying that VSS, for example, can be counted as space flown as well, according to the FAI criteria. Out of that 602 people, 27 flew beyond the Earth orbit, and that involves missions to the moon. 12 people landed on the moon. And another thing I would like to stress, speaking of the statistics, is this year we have experienced another kind of record. On 31st of May of this year, there were 17 people altogether in space, and that included the International Space Station. and Chinese Tiangong space station, which had, I think, crew handover at that time, so that amounted to 17 people altogether in orbit. Speaking of the duration, like what we can do, the longest mission was 438 days long. It was flown by Valery Polyakov in early 90s on board Mir space station, a year and a half. Speaking of the maximum cumulative time in space, it's 878 days. And this belongs to Gennady Padalka. I think he flew 5 missions, but all 5 missions were long duration ones, and his flight career started on Mir. And the maximum duration of stay on the moon is 75 hours. That's the final Apollo mission. So it's kind of fascinating looking at the moon, thinking that someone lived there for 3 days. And if you're interested in statistics, there is a link to the website where you can learn all those things, plus many more details about who flew, for how long, on board which vehicles, and so on. As a major goal of our meeting today, I believe is to integrate the information you have acquired over recent week, because you've been to Zvezda, you've been to Energia, you've been to Air and Space Center at the exhibition, at the Old Russian Exhibition Center, and you met astronauts, you met cosmonauts, and you've got that information. And I just wanted to show you how all those things come together in a single story of human spaceflight. And at this point, I would like to talk about the possible ways to get to space. And since that moment, we'll be talking about the orbital flight. And from the physical standpoint, once we are called space development theory and practice, we would like to talk about the theory and how to bring it to practice. Well, from the theory standpoint, I will not be torturing you with the formalisms and deriving the magnitude of the orbital velocity, which would be roughly 8 kilometers per second at the sea level. And the question is how we achieve that kind of velocity. And to set aside all kinds of fantastic things like using lots of swans, towing a chariot with a pilot or something of that sort. So theoretically, there are several ways to achieve that velocity. All of them are theoretically, but so far only one is practical. Because theoretically, you can use active acceleration, just maybe like a huge cannon, for example, to accelerate your vehicle to the orbital velocity, or to use a space elevator. And both of the concepts are theoretical and theoretically working, but impractical, because in the first case, you need to accelerate from 0 to 8 kilometers per second over, I would say, hundreds of meters, which creates an unbearable acceleration for any living creature. And for the other, in the other case, the elevator needs to sustain its own weight, which has not been practical so far. So the only practical way to fly to space is to use the jet propulsion, to use the reactive forces created by the rocket. And at this point, I'll stop talking about the theory and we'll start talking about the history. And this was understood in late 19th, early 20th century by many people. And some of them actually got down to developing the practical means what I mean here in particular, developing rocket engine, developing the first small rockets. Those people were getting together in the groups and developing and testing their first simple designs. And two persons on this slide can be believed the major influencers of the human spaceflight in 20th century. And on the left is Sergei Pavlovich Korolev, who was a chief designer and the mastermind of all the achievements of the Soviet Union in space in 1960s. And Wernher von Braun, who performed pretty much the same role on the other side of the globe. So Korolev studied in Bauman, graduated it in, I believe, 1937, something of that sort. And his initial idea of using rockets was to apply them to airplanes, because he trained as an aeronautic engineer, and by the moment he graduated, he had several designs of the gliders which were built and flown, including a glider which was capable of making a loop. He also thought that putting the rocket engine into a glider will make it possible to raise very high and prolong the flight. So that was his initial idea, but later on he got together with the group, which was called Group for the Rocket Propulsion Studies, scientifically led by another famous person, Frederick Zander, who was mentioned in one of the lectures. And he applied his idea to his engineering skills to rocketry. I will not describe his subsequent life. It was not easy. He actually suffered from Stalin's purges, from people reporting on him for doing what he didn't do. But I would actually continue the story of Korolev at mid-1940s, when he actually faced the designs of the other person on the right side of this chart. Wernher von Braun was essentially, I would call it, a rich rocketry enthusiast in Germany, starting with 1920s, and Germany had a particular interest in rockets because as a result of the World War I, Germany was extremely restricted in terms of artillery, aviation, fleet, etc. So this was the new enabling technology to build the weapons without any kind of control. So German military understood that potential very quickly. So they paid a lot of attention to the group of von Braun, which was building their small rockets. And when Nazis took the power in Germany, they emphasized those studies even more. So as a result, being 23, von Braun became head of the rocketry program for Nazi Germany. That resulted in making the first operational ballistic missile actually operational in 1943. I'm talking about V2, capable of delivering a payload of 1,000 kilograms to a range of about 300 kilometers. A significant remark here is that more people died producing those rockets than died from their employment, because the production facility was actually a concentration camp where the prisoners were building those rockets. So as a result of the World War II, Braun and his team of engineers surrendered to the United States of America and moved to the US and continued their studies there. And Sergei Korolev was made a part of the group to study German rocket technology in 1945. and he went to the Russian. Went to Germany to study the German German experience in the field of the rocketry, and he had a very specific task from the government of the Soviet Union to recreate and to start the production of the Russian version of V2 in the Soviet Union. However, here we should, like, from the historical standpoint, we can say that the US has got, despite of having its own school of rocketry, which existed by that moment, they acquired German rocket technology in a single package. So they had von Braun, they had the key persons, they had documentation, and so on. Korolev had to essentially go through that school with his engineers, and they needed to dig deep in what they've seen, and they had some fragmental knowledge initially, but they actually got it through. And in 1947, they commenced the first test of the rocket called R1, which was the Russian copy of V2. You may ask me a question, why was it a copy? That was the direction from the very top of the government. Actually, that's the next part of the story. To build an exact copy of V2. Just no step to the right, no step to the left. However, that gave Korolev's team, which was called OKB-1, Special Design Bureau 1, a great experience, and they actually perfected the design. They made the rocket called V2, which was way more advanced than V1. R2, which was way more advanced than V2, for the reason of using the new structural solutions, upgraded engine, and some other innovations, which made it possible to increase the range, to increase the payload. So the final design from that V2 derived rockets in the Soviet Union was called R5. It could fly to the range of 1,500 kilometers, and it could carry a nuclear warhead. So the range was not sufficient for the requirements, for the geopolitical requirements, and the Soviet Union was in a pretty complicated situation there because the opposition, I would put it this way, had the air bases throughout Europe, so they could use the bomber planes, and Soviet planes had to fly across the North Pole to complete their mission. So some kind of asymmetrical decision was required, and particularly from that standpoint, we started looking for the solutions how to deliver something to the range of 8,000 kilometers. And there was a number of designs. It included cruise missiles, it included ballistic missiles, but what actually won that competition, you can see it on the chart. This is the rocket you've seen in our display facility in Oriva. And I don't know if you were mentioned, but this is actual R7, serial number 11 on that display. So that's a real missile, which could fly to 8,000 kilometers with the warhead of 5.5 tons. Which, if recalculated to the orbit of 200 kilometers, gives you a payload of about 1.5 tons. So it's never been documented somewhere, but some sources are saying that warhead mass was quite excessive, and that's a result of the deal of Sergei Korolev with some of the developers of the warhead to give more conservative requirements so that he could use R7 as a launch vehicle for satellites afterwards. So that launch vehicle made it possible to launch the first Sputnik in 1957, which it reached the orbit of about 800 kilometers, and it was a sphere weighing 83 kilograms, which had temperature sensors and pressure sensors inside, and 2 radio transmitters, which were transmitting those data to the ground by varying the frequency of the beeps emitted by those 2 radios. So the more frequent beeps were, the higher the temperature were, etc. The first US satellite called Explorer 1 was launched on February 31st, 1958. On the launch vehicle, you could see here, it is called Juno. It's derived from one of von Braun's designs called Redstone, and actually Redstone played a fairly important role in the US space program, as we will see later. So despite of having a mass of 4.8 kilograms, and proving the concept Mr. Krikalev has just outlined, that doesn't really matter what you're doing. What matters is your purpose, your task. Explorer 1 did accomplish a very important task. It discovered the radiation belts around the Earth. So that technology keep evolving, and multiple satellites were launched. The first payloads were launched towards the moon, for example, but it seemed to be that the next logical step in space exploration would be to launch the first human to space. And first, I'll tell you about the approach which was taken here in the Soviet Union, and then we'll talk about the approach taken by our American colleagues. Of course, 1.2 tons didn't seem to be enough to launch the orbital mission. The reason why I say seem, because we haven't seen the US design yet. So by that moment, the third stage for R7 was developed, which enabled the launch vehicle to carry 4.7 tons to the low Earth orbit. So the designers of the spacecraft on the right had to comply to the mass budget of 4.7 tons. And what we can see a spacecraft called Vostok. I don't have a mouse here, and my pointer is too weak to shine on that screen. But if we talk about the design, we can see that it's got the spherical section, and the spherical section is actually the re-entry capsule for a single crew member who was laid out inside the capsule in the seat you've seen in Zvezda, wearing the suit designed by Zvezda and seen in Zvezda as well. So the section consisting of 2 cones underneath the capsule is an assembly and instrumentation compartment, which carried a propulsion system, some avionics, some auxiliary systems, motion control system. So basically all the systems which enabled the spacecraft to fly. And the idea was to separate the capsule at a certain point, and that would be a single component of the vehicle returning to the Earth. So we'll talk a little bit more about the about the flight scheme on the second chart, but at this point I would like to say that Vostok involved 6 missions flown, starting with the first one, Yuri Gagarin. Then a day-long mission flown by German Titov, a mission which involved 2 Vostoks flying at the same time at the distance of 2 to 3 kilometers away from each other, flown by Andrian Nikolaev and Pavel Podboevich, and the mission flown in the same fashion, including Valentina Tereshkova, the first woman cosmonaut on Vostok 5, and Valery Bykovsky on Vostok 6, who flew for 120 hours, which was a record at that point. Let's talk about the flight technique and let's find out why we needed the ejection seat. As you can see here, the launch vehicle with the spacecraft launched and flew in a fairly normal station, in a fairly normal fashion, separating the first stage, then dropping off the nose fairing, then the second stage would separate. And actually, here is an important point, is that the orbital altitude was actually commanded by the moment of separation of the second stage. Because the third stage would burn for the constant time until it placed the spacecraft in the orbit, into the orbit. Then the orbital phase would follow till the moment to return was coming. The spacecraft was separated into the capsule and the assembly and instrumentation compartment, and they were making the re-entry, rendering only the capsule alive, because the assembly and instrumentation compartment had no thermal protection. Then the capsule was falling ballistically, which was resulting in G loads of roughly 10, 11 G. So it required really strong people to fly until the parachute started deploying at 7 kilometers. And then the most interesting portion, which is kind of obscured by my image in the lower right-hand corner, was coming. And let me explain why was it happening. At an altitude actually, I was wrong. I was wrong saying that the main chute was deploying at 7 kilometers. Prior to doing that, cosmonaut had to eject from the capsule. Why was that required? When you listen to Alexander Lazutkin in Zvezda, he described you extremely vividly what it takes landing on the hard surface with no soft landing thrusters. So Vostok didn't have soft landing systems. Such a technology did not exist at that point. So being inside the capsule at the moment of landing created quite a lot of the possibility that you will be damaged. In the way we Russians say it, that you will not collect all your bones together. So the idea which was used here was to eject a cosmonaut from the capsule, deploy the pilot chute, let that system fall to 4 kilometers, then separate the pilot from the seat, and let the pilot land under his own main chute, which was quite feasible from the impact load standpoint. Besides of the fact that you were wearing a spacesuit and you were carrying a survival kit, so making all the system weighing roughly 100 and something kilograms. So that fact was kind of concealed over a very long period of time. And the problem was that International Aeronautic Federation would only count a record according to its existing practice. based on the on recording the results of various achievements in aeronautics, flying planes essentially. So the requirement was that the pilot was to remain in the aircraft at the end of the mission, meaning that he didn't bail out, and it didn't take into account that this ejection might be a part of the nominal procedure. So for a very long time, it was stated that Gagarin landed in his capsule, inside of his capsule. However, if you would have read the memoirs, it would say when the parachute opened, I looked up, I've seen the blue skies with some small clouds over myself. Wait a minute, could you see it from the capsule? So anyway, that mission was flown, and just to tell you what it involved, why Gagarin received all his honors, I'll tell you that the mission did involve 13 of nominal conditions. So the man was really going into the unknown. Besides of all those speculations, what happens to you in prolonged zero-G? Are you going to be sane? Are you going to be insane? He was flying the system. The engineers were designed to be reliable, and actually those efforts actually paid because the mission was a success. He came back alive. But here is what happened. I told you that the orbital altitude was actually pre-programmed by the moment second stage would shut down. And if we come back to the previous slide, to the conical section, I would say that conical section only had a single engine. And that single engine was to provide the deorbit burn. Question is, what would happen if it didn't start? So the designers said, well, we don't have any mass budget for the second engine, but we will launch Vostok to such an orbit that the remaining atmosphere, the remaining atmospheric drag would naturally deorbit the vehicle within the lifetime of the life support system, namely within 10 days. And this is how the orbit of Vostok was calculated. So, however, the second stage had two mechanisms to shut it down. The first one was based on integrating the acceleration. So until that value was reaching the certain limit, then the signal to shut off the main engine was sent. And the second layer of protection was the timer, which would count to the certain moment and then send the signal to shut down. So for some reason, that integrator didn't function properly on that mission. So the second stage shut down from the timer. And when the orbit was measured, it appeared that it is way higher than it would involve the natural deorbiting in 10 days. So it was roughly a month-long mission. So here is the first problem, over-insertion. The second problem came at the end of the mission, at the deorbit, because the deorbit burn was actually shorter than expected. Due to a malfunction, the valve in the propulsion system was leaking, so the engine didn't have enough propellant to make the full burn. However, that burn was enough to deorbit the spacecraft, but not gaining the desired delta V resulted in a sequence of the other problems with the separation. Certain automatic systems didn't send their signal to jettison the capsule from the assembly and instrumentation compartment. The whole spacecraft re-entered, heated up, and then the thermal sensors sent the signal to separate the capsule. At that point, it was already known that we can't see it here, that a very massive bundle of cables and pipes connecting capsule to the assembly and instrumentation compartment would not separate because of the schematic error. However, the previous unmanned launches did prove that the capsule lands anyway, because the cables would burn at a certain moment and the capsule would separate. So the designers decided not to fix anything, not to spoil anything. So, and that like Dumbbell-like configuration re-entered. It was oscillating for some time, and that was reported by Gagarin at a certain moment. Then everything went as expected. Besides of one fact, once the orbit was higher and the deorbit burn was shorter, he was landing somewhere he was not originally supposed to land. That's why instead of landing in northern Kazakhstan, he landed in Saratov region outside of Engelstown. And he lost the very final phase of his adventure when his main chute deployed. He looked down and he saw Volga River with all the chances to land on the water. And despite of having an extensive training on this kind of scenario, he didn't really want to have a swim wearing a spacesuit with the life support, actually with the survival kit. So the decision he made was to get rid of the extra mass, and he severed the tether to that life support pack underneath him. So he managed to overshoot the river, land in the field, and that was the end of his mission. And here we can see the launch. Here we can see Sergei Korolev saying goodbyes to Gagarin, and Gagarin, after the completion of his mission, greeted by the soldiers of the military unit who actually recovered him in that field. So that was the mission, and that actually proves that it involved a huge risk. And that explains why Gagarin is believed to be, well, actually, all the Russians, I believe, think of Gagarin as heroes. And I would say for the non-Russian participants, I would say that Gagarin is something absolutely indisputable for us. We can discuss anything. We can discuss certain shortcomings of our life. We can argue about the certain portions of our history, but Gagarin is absolutely above everything. His role is as indisputable as the New Year, for example, which is everyone's holiday. So let's, this is what you've seen. I think you've seen it in Rocket and Space Corporation Energia. That's the prototype of Vostok spacecraft used for engineering testing, and the capsule flown by Gagarin with his training suit. On the US side, the approach was quite peculiar. I told you about the role of Redstone for the human space program in the US, and the problem was that the US didn't have anything similar to R7, at least at that point. So the race for the first human in space was kind of lost. The different approach was taken. So we can't really explain why. We can kind of speculate about that, but the decision was made to perform the first US mission to space in the shape of suborbital flight. That did not involve entering the orbit, but going over that 100 kilometers line, flying parabolic trajectory in the same way the warhead of the ballistic missile would fly and then splash down in the ocean. Two missions like that were supposed to be flown, and then they would transition to the orbital phase, because by that moment they expected the new missile called Atlas to become operational. That would actually enable NASA to fly the first orbital mission. And I told you that 1.5 tons seemed to be insufficient for the human mission here. The guys managed to do it in 1.3 tons. The first US piloted spacecraft was called Mercury. It was designed for one person. You can see that the design approach was quite different. So that's the first design which actually involved the escape tower as a part of the crew escape system. So six missions were flown, two suborbital ones. The first one on the 5th of May 1961 by Alan Shepard, and the first orbital one on 20th of February 1962 with John Glenn. Mission duration up to 34 hours was achieved on this kind of vehicle. And that actually gave a lot of experience in terms of the space flight. On the left, you can see a suborbital version on a Redstone booster. And on the right, you can see the orbital variant on top of Atlas launch vehicle. Actually, Atlas, it is kind of interesting to mention that we can say that both R7 and Atlas survived the entire history of the human spaceflight so far. And if we talk about Soyuz 2, which is a kind of descendant of R7, not to the great extent. And you can see a lot of genes from R7 there. Atlas, there is still a rocket called Atlas 5, Atlas 3. It does have some genes of original Atlas, but that's an essentially different vehicle. The next the logical step was to launch a crew of multiple crew members and to perform the first EVA. So the first task was accomplished on the spacecraft Voskhod 1, which was very similar to Vostok, but it had an additional rocket pack to be used as the backup deorbit system. The decision was made to get rid of the spacesuit because it was believed, based on 6 missions flown, that the capsule is absolutely reliable and will never depressurize. At that moment, the technology of the soft landing was developed, so they could get rid of the ejection seat and use 3 Kazbek seats you've seen in Zvezda laid out inside that spherical capsule to carry a crew of 3. And that was flown in October of 1964 by Vladimir Komarov, Konstantin Feoktistov, actually the first civilian cosmonaut, interestingly enough, being a general design person for Vostok and Voskhod. The legend says Korolev summoned him and said, well, you need to fly and you need to try what you have designed. And a physician, Boris Yegorov. We've seen the spacesuit used on the first spacewalk by Alexei Leonov from Voskhod 2, and that was performed from the same kind of spacecraft on the 5th of March 1964. There is quite a lot of discussion about how that mission was going, but I would rather use some kind of opportunity on the side to discuss those particularities. To make the long story short, I would say there were some difficulties with the rigidity of the suit enclosure, despite of having a very strong crew member selected for that mission. And just to give you an example, Alexei could actually squeeze out 96 kilograms with his palm. The suit appeared to be very rigid and, to my mind, slightly oversized. So the rigidity resulted in the problems of entering back the airlock in the technique which was prescribed by procedure. And you were to go your feet first in order to be able to see how the hatch is closing behind you. So Leonov took all the possible efforts to do that. Then he decided that he's going to really reduce the operational pressure in the suit from 0.4 bars to 0.27 bars. And that was actually a risky but pretty much thought out decision, because it was supported by the idea that he already spent an hour breathing with pure oxygen, so he had no nitrogen in his blood, and the decrease of the pressure did not result in bends. The suit got softer, but still it was impossible to enter feet first, so he entered head first and then somehow turned around inside the airlock, which he couldn't replicate afterwards on the ground. So the outcome of the mission was also kind of adventurous, because the automatic system failed to initiate the deorbit burn in the proper moment. The crew was commanded by the ground to do it manually. I'm kind of skeptic about the precision of the human pressing the certain button or throwing the certain switch at the given moment of time with the fractions of the second precision. So apparently this fact and some design particularities of Voskhod, which actually called for leaving your seat in order to send that command, which is probably offset the center of gravity, etc., resulted in the crew landing in the deep forest nearby city of Perm in Siberia. It was very cold, trees were very high. Search and recovery had to use a lot of time to find them. So the crew actually spent about a day in the woods prior to the first search and recovery party reached them. And they actually had to ski out of their landing site to a spot where the helicopter could land. On the other side of the world, people started doing something else, and that was based on the decision to go to the moon. And the lunar program will be covered by Mr. Revy in his presentation afterwards. So I'll tell you what preceded that and briefly what it took, but the details will be given by Mr. Revy. So in order to prepare for the lunar program, it was necessary to master the certain technologies. For example, to be able to stay in space for the X amount of days sufficient for the lunar mission, to be able to dock and undock, to rendezvous, to perform an EVA, and in order to develop and master those technologies, the spacecraft called Gemini was developed. It was a twin-seater spacecraft. Interestingly enough, the ejection seats were used on this design instead of the escape tower. And if you recall Mercury, you can see some legacy of Mercury in terms of shape of the capsule. And to be true, initially it was called Mercury 2 or something of that sort. But probably the Russian experience was also taken into account, and Mercury acquired the service module, which was carrying the propulsion system, the thermal control, and the other equipment which didn't fit the capsule. Another interesting feature of Gemini was that it flew on Titan II, which was a real ICBM, operational ICBM, and astronauts who flew it really feel a very rapid acceleration upon the launch. So in the center, you can see the launch. What in particular was accomplished on Gemini? There was a series of Gemini missions which involved rendezvous and docking with a special docking target called Agena, which was an upper stage for another launch vehicle, either Atlas or Thor, which was capable of performing maneuvers. So Gemini had the docking mechanism and the docking radar to hook up mechanically with Agena. So they were practicing the rendezvous maneuvers. The first US EVA and the series of EVAs were performed from Gemini. And you can see the first US EVA performed by Edward White. The long duration mission, which was, I think, 2 weeks long, was flown on Gemini 7. And interestingly enough, it involved a rendezvous of Gemini 6 with Gemini 7 for the reason that the docking target failed to enter the orbit. The program management thought a little bit and said, well, why don't we use Gemini 7 as a docking target for Gemini 6? And of course, they couldn't dock, but they were flying information, flying around each other. So that was also done. And here we come to Project Apollo, which will be covered by Mr. Rebbe later. I'm sure I'll just give you some basic ideas that in order to fly to the moon, NASA had to build a launch vehicle called Saturn V with a mass of roughly 3,000 tons. And the system involved 2 spacecraft, command and service module and lunar module. So the cluster of the vehicles was supposed to be inserted into the translunar trajectory by the 3rd stage of Saturn V. Then the command and service module engine was used to shape the circumlunar orbit to put the cluster into the circumlunar trajectory, and then 2 crew members out of 3 would land on the lunar surface in the lunar module, which was consisting of the descent stage and the ascent stage, and upon some activities on the lunar surface, come back to their crewmate in the command and service module, discard the ascent stage of the lunar module, and return back to the Earth in the command module. So in total, the program involved 17 missions, which resulted in 6 landings on the moon. As I mentioned in the beginning, the maximum duration of stay on the moon was 75 hours, and 13 astronauts visited the moon. And the first one was whom? Neil Armstrong, followed by Buzz Aldrin on 20th of July 1969. And here you can see actually the scale of the Enterprise. You can see Saturn V, a truck, and the bus parked nearby. at this point, yeah, you can see the assembly facility, the way the two vehicles were laid out on top of the launch vehicle. But here I would like to stop for a minute to tell about the specialties von Braun brought into the US space program and the differences, actually. On the left, you can see a mobile launch pad transported by the mobile transporter. It's kind of hard to see, but there is a vehicle which has got Caterpillar tracks, which is moving the entire system of the launch table, launch vehicle, support tower, servicing tower, along the road to the very launch. That you need to build, test, and fly the rockets in the same attitude, which might make sense from the standpoint that in order to put the vehicle horizontal, you need to put additional structural members just to make it strong enough to sustain its own weight while it's horizontal, while it's rotated vertical. But this kind of approach resulted in this. And speaking of Apollo program, I just want to say that Apollo 11 was the first one to land on the moon on 20th of July, 1969, as it was promised by President Kennedy by the end of the decade. You can see, I think, Armstrong's track on the lunar soil, and Buzz Aldrin on the left. And it finished with Apollo 17, which spent 75 hours on the lunar surface. And by that moment, the astronauts were actually able to travel along the lunar surface using this rover to make some field trips to study the geology of the moon. It was a mission which actually involved a crew walking from Apollo 12 lander to an unmanned probe called Surveyor to dismantle some equipment from the probe and then bring it back to the Earth. But this will be covered in detail by Mr. Reby afterwards. And speaking of results, definitely lots of images of the moon shot from the close proximity. For about 400 kilograms of the lunar soil samples, which actually give some insight on the origin of the moon, and actually origin of the Earth. Speaking of the Soviet piloted lunar program, it had a long story and it was not a success. It involved the use of a kind of counterpart of Saturn V mass-wise called N1, which was only capable of launching 90 tons into the low Earth orbit compared to 130 tons to Saturn V, which resulted in tremendous mass constraints for the designer of the lunar vehicles. The crew size had to be reduced from 3 to 2, enabling only one crew member to land on the moon, which created a lot of problems security-wise. Multiple stages were to be used for various phases of the mission to optimize that structural ratio of structural mass to propellant mass, trying to squeeze everything out of that formula. So what seems to be functional today didn't function at that time. For some reasons, I will not expand on. 30 engines were to be used on N1 first stage, which is the case for Falcon Heavy now. Not 30, but I think something close to that. And we've got the flight control system which can manage all those engines these days. At that point, it was the first time it was attempted to be done. It wasn't perfect. Some, I would say, political mistakes were made regarding the testing, because the first stage was never tested on the ground. It was supposed to be tested in flight. So there were 4 missions flown by N1, resulting in the maximum duration of flight of 100 odd seconds, very shortly, seconds prior to the separation of the first stage, but it didn't work. It also resulted in destruction of one of 2 launch pads in Baikonur by the vehicle, which has lifted by 12 meters and then shut all the engines off and fallen back on the pad. The other components of the system, such as LK lunar lander you've seen in our display facility in Oriva, were designed, and LK was even tested in space, launched on top of Soyuz launch vehicle. Krechet spacesuit you've seen in Zvezda was also designed and operational. This piece of equipment called LOK, Lunar Orbital Vehicle, was also designed and tested according to some of the sources. And to give you the scale, here is N1 on the pad, being installed on the pad, N1 in the assembly facility, the design of the Lunar Orbital Vehicle, which is very similar in its philosophy to Soyuz, a vehicle we are still flying, and the LK lunar lander we were able to touch and maybe climb in Oriva, right? So one of the pieces of the engineering legacy from the lunar program was a design of the vehicle which was to be used to prove the techniques similar to the ones proved by Gemini, and it appeared to be a long-living vehicle called Soyuz, because we've still got a vehicle with the same name, heavily upgraded, maybe just the portions of structures remain from the original Soyuz, but it is still Soyuz. So, and Soyuz was launched by another version of R7 called Soyuz, which was capable of launching 6.8, actually, 6.8 tons. Using kerosene and liquid oxygen in the same way. So this is what original Soyuz looked like. It had a capsule in the center. It had assembly and instrumentation compartment with the avionics container and propulsion system on the right, and the habitation compartment on the left, which could be either used as an extravehicular activity airlock or as an additional compartment for crew habitation. For example, to sleep, to have a meal. The waste management facility was also there. Actually, these days, Soyuz is considered to be an extremely reliable vehicle, but its history started with the flight accident. It was not the first occasion when people were lost during the spaceflight operations. I didn't tell about Apollo 1 crew, which burned during the fire while preparing for their mission during one of the tests. A sad story of Soyuz involved an incident with Vladimir Komarov on 24th of April, 1967. So when the parachute system failed and the capsule with the cosmonaut crashed into the ground. There was another incident with Soyuz I will talk about a little bit later. So here are the capabilities of Soyuz, and it flew several standalone missions, but it proved itself in combination with the other pieces of equipment. The matter is that in 1967, a launch vehicle called Proton was tested, and that was a launch vehicle which was capable in launching 21 tons into the low Earth orbit in three-stage configuration, which actually made it possible to implement the concept of space station. Why we need a space station? Doesn't matter what we fly, whether we fly Soyuz or we fly Apollo, we are dealing with the limited volume inside and the limited payload capability. So first, we can't carry significant experiments. We can't even carry the facility to counter the effects of the zero-G on the human body. So having that large payload capability makes it possible to establish something similar to what you are working on in the team project. Some kind of facility in orbit, which would have everything which would be required for living, for making the experiments. And then the transportation vehicles like Soyuz could fly to this kind of space station to rotate the crew. So the first station, Soviet station called Salyut, was designed like this. It was launched on Proton. It had Soyuz to deliver the crew to the station and bring it back, rendering the station unmanned between the missions. And it was launched in 1971. The first expedition to the station was a failure due to, I would put it, inability to dock, due to some kind of, I wouldn't call it ignorance, but missing a very obvious fact from the control theory. So the problem was that the crew of Vladimir Shatalov, Alexei Yeliseyev, and Nikolai Rukavishnikov was to dock to Salyut space station. And they performed the rendezvous, and by the way, those booms on top are a part of the automatic rendezvous system, which actually feeds the data on the relative motion of Soyuz and station to the Soyuz control system, and Soyuz fires the engines and thrusters to come to the docking cone. And that was accomplished. However, so Soyuz was flying, being controlled. So the motion control system controls the lateral motion and the attitude. And the station was maintaining its attitude as well. So when the docking probe hit the cone, it actually influenced the station control system, which thought it was an external disturbance, and started maneuvering back. And while it was maneuvering, the probe slid into its latched position, and the station was still trying to stabilize itself. So as a result, the probe was bent. And when two docking rings started being pulled together, they couldn't close, the seals could not compress, the micro switch could not activate, the docking cycle was incomplete, so the crew couldn't dock. And it appeared that unless you can complete the docking cycle, you cannot start the undocking cycle. So it involved some hacking on board, of course, with some recommendations from the ground, getting to the certain wires, twisting them together, and thus undocking, rendering the docking port still operational. For the next crew, the crew of Georgy Dobrovolsky, Vladislav Volkov, and Viktor Potsayev, which was successful in docking and which worked for 21 days, as far as I can recall, on board the station, but who suffered from the engineering mistakes taken on Voskhod, because the missions were flown without pressure suits. So that crew of Soyuz 11 was lost in 1971 due to the capsule depressurization, which actually called for some stop in Soyuz missions, Soyuz redesign, and you've seen Sokol suit, you've seen the seat. Actually, the crew had to be reduced from 3 to 2 because the rightmost position was to be taken by the life support pack for the suits. Here is an answer why Sokol has got that interesting helmet design with the soft helmet, because it was designed to lay out the crew member in the seat which already existed. And speaking of Salyut space stations, we can say there were 3 generations, and I would like you to look at this table. Maybe you will have questions, and I'm expecting at least a single question from the table in the end of the lecture. So the whole development of Salyut space station was that Salyut 1 design did not have the rotating solar arrays. That was in controversy with science, because you could either generate the power or look at the stars, or vice versa. So the larger and orientable solar arrays were introduced on Salyut 2 and Salyut 4. The altitude station flew was also increased. That would increase the duration, the orbital lifetime. Here I would like to say that Salyut 2 never flew with the crew. It was launched, and for some reason it lost the pressure shortly after the orbital insertion, maybe due to the collision with the micrometeoroid or the orbital debris. So there is no exact cause identified. And Salyut 4 was successful, and the mission duration of 63 days was achieved. The next design, Salyut 6 and Salyut 7, were, I would say, revolutionary, to say the least. And what has revolutionized that design was the second docking port, which actually enabled to resupply the station with the special cargo transportation vehicles called Progress. Progress could carry fuel, oxidizer, compressed gases, water, dry cargo, which could be used by the crew on board the station. Progress could also be used to reboost the station, increasing the lifetime in orbit almost infinitely. And you can see that the upgrade to Soyuz vehicle called Soyuz T came to life, and that was the first Soyuz with digital computer as well. So having all those capabilities made it possible to fly Salyut 6 and Salyut 7 in the permanently piloted mode, because the second docking port enabled to rotate the crew, to bring the new crew in, to have a handover, and then to return the crew which was flying the station back to the Earth, leaving another 2 or 3 persons on board the station. We can't see the mission duration here. I would tell you it was 180 days, which was actually something typical these days. Fred Hayes mentioned Skylab and questions were asked. I don't have much time, but I should explain what it's all about. Apollo program had some initial idea of flying, what is it, 1917, 19 missions. 80, actually 20 missions. But once the political goals were accomplished, almost all the science which could be collected was collected. The decision was to shorten the program by 3 missions. So Apollo 17 was the final one on the moon so far. And looking at the counterpart of on the other side of the Earth, flying Salyuts, NASA engineers said, why don't we build our own space station? How can we make it quickly using the already existing equipment? Let's take the third stage of Saturn V. It has already got the two pressurized volumes, an oxygen tank and the hydrogen tank. Let's convert the hydrogen tank into the living quarters, and we'll use the oxygen tank to collect all the garbage which results from the mission. So if Soyuz is a bus, Saturn was a tower with multiple levels. People who flew it just said it was even way too spacious. So it was mentioned yesterday that it had all the thinkable amenities for the space flight at that moment. It had shower, it had individual living quarters for the crew members. The whole scientific purpose of Skylab was astrophysics, and it was equipped with this windmill-like package of instruments with the individual solar rays powering those instruments. It was also equipped with the docking compartment, docking adapter it is called here, and the airlock, so that the crew could perform extravehicular activities from the station. Have a look at the second docking port. The second docking port is not to rotate the crew, but to be able to rescue the crew at a certain point. Apollo Command and Service Module was to deliver the crew and bring it back. The station was launched. Here is the summary of the specifications. You can see it was quite heavy. 3 expeditions were flown with the duration from 28 to 84 days. And the beginning of the mission, this is how the station looked like in the real life from the approaching Apollo. Question would find the differences between this one and this one and try to explain them. What is that blanket covering the station? Why does it have a single solar array instead of 2? The first expedition to Skylab was a real adventure for the crew which was flying it, due to some problems which occurred during the orbital insertion of the station. You can see on this diagram a component which is called micrometeoroid shield on the right. So the portion, the white portion of Skylab, if you look at the photo of the launch vehicle, was not covered by the nose fairing. So it was subjected to all the atmospheric loads during the insertion, and apparently it was not strong enough to sustain that drag. So atmospheric drag tore apart one of the solar arrays, damaged that micrometeoroid shield, which was made of the thin aluminum plates, which were mounted on the bimetal pedestals, which being heated up in orbit would move those plates away from the main structure of the station. And unfortunately, that was polished aluminum, which was to be a thermal barrier as well. So when the station inserted the ground, the Mission Control Center observed almost no electric power on board and observed the temperature growth in the habitation compartment. So, and they actually had to speculate what might happen, but so apparently they used some military optical facilities to have a look at the station and something of that sort. But the conclusion was that main solar arrays did not deploy. The station has somehow lost that micrometeoroid and thermal shield. Expedition 1 has got to be repurposed to fix the station first and then to fly it. So, and Max Zaitsev showed you a Marshall neutral buoyancy simulator, and this is where all those techniques were mastered, because the crew was trained for an extra week to work on the solar array deployment mechanisms, to deploy this temporary, which became later permanent, thermal blanket. And the design is very interesting because it's actually like an umbrella, which was initially folded, stuck out through the small equipment airlock, and then deployed. And as for the second solar array, the crew had to perform an DVA and free the deployment mechanism from the piece of aluminum, which was Gemini. So, and that made the station operational. To put it through, the temperatures inside were not that high to kind of spoil the food in the local refrigerators. It was kind of stuffy, I would put it this way. So the crew had to spend the first night in the airlock, and then putting the gas masks, enter the station, and they found the station was quite flyable. So they proceeded with their EVAs and they made it operational. So the first mission, which actually involved cooperation in space, was Apollo-Soyuz test project, when Apollo 18 was flown together with Soyuz 19. The engineering goal was to test the universal docking mechanism, which was capable of working as a passive one and an active one. Mission involved 2 dockings with Soyuz in active role and Apollo in active role, some experiments. Here you can see the crew. The terracotta suits are worn by Apollo crew, green suits are worn by Soyuz crew. It was Tom Stafford, Dick Slayton, and Vance Brand on the US side, and Alexei Leonov and Valery Kubasov from the Soviet side. And you can see the configuration of the cluster. Soyuz and Apollo had different atmospheres. Apollo was using pure oxygen at the pressure lower than atmospheric. Soyuz is using our common nitrogen-oxygen atmosphere with under 1 bar, essentially. So a special airlock in the center was to be used in order to enable the crew members to pay visits to respectively Apollo or Soyuz. We talked about the reusable systems today. Questions were asked, and in 1981, the first ever reusable space station called Space Shuttle was made operational. It consisted of the orbiter, which carried the main propulsion system and was a second stage for itself. Solid propellant, solid rocket motors, which were making up the first stage, and that orange propellant tank, which was carrying oxygen and hydrogen for the main propulsion system mounted on shuttle orbiter. You can see the capabilities here. Here I would like to show you the design of the orbiter itself. It had a cargo bay which would carry satellites or the modules of the space station to the orbit and return them back. And actually, it's not really a secret that Space Shuttle was initially designed to build the space station, because historically, station program and shuttle program were conceived at the same time. The station just took longer, and I would say was more problematic. But as we could see from the ISS construction, shuttle did perform its role and did what it was supposed to do finally prior to the end of its operation. So besides of that, the orbiter had wings, had rudder, had a remote manipulator system, had 3 sets of thrusters for the attitude control in the nose and in the tail, had a manipulator arm to operate the payloads, and it relied on the legacy of Apollo, both philosophically and materially, because the launch pads from Saturn V and the mobile transporters, which were used for Saturn V, were inherited by space shuttles, and they flew from the same pads. Here is the launch and landing, and 135 flights were made over the period of operation of shuttle systems. Shuttle program involved 2 serious accidents, which resulted in the loss of 2 orbiters out of the fleet of 5 and the loss of 14 crew members. If you're interested about that, you can talk to me on the side because time is running out. The technology of Mir space station evolved into the technology of the space stations evolved into the first modular space station called Mir, which was launched in 1986 as the first module, as a core module, and grew up to the station you can see on this chart, with the mass of 120 tons. Mir was probably the first truly international space station because the representatives of 12 countries worked on board Mir. To put it through, some international missions were also flown on Salyut 6 and Salyut 7, but Mir became a platform for a huge program, for the first phase of the huge program called International Space Station. So Mir started with a single core module launched in 1986, and then was built up with Quant module, Quant 2, which created a pretty much torturous configuration for the motion control group, because the center of mass is offset, your thrusters are still in the same location, and how do you control such an asymmetric body? But they did manage to do that. Then the T-shaped configuration with crystal module, so Quant making L was an augmentation module which brought a dedicated airlock and some life support facilities to the station. Crystal was essentially a material science experiments module. Then it came to some kind of stop in development till early 1990s, till 1994, 1995, when the program called Mir NASA started, and two modules, Spectre and Priroda, were launched towards the station, and they carried mostly NASA payloads to support the program. And what that program involved, the missions, long duration missions flown by the US astronauts on board Mir space station. You talked to Bonnie Dunbar at the opening, after the opening ceremony. She mentioned being a backup to Norm Taggart, the first NASA astronaut who flew Soyuz to Mir space station. And you can see Norm on the left and Bonnie on the right from the blue-suited person on that mission. So the person with guitar is Gennady Strikalov, Bauman graduate who studied at M1 department and actually flew, he said, 5.5 missions to space. The half of the mission was a launch accident in 1982 when he and his Soyuz commander, Vladimir Titov, had to use the emergency escape tower to evacuate from the burning rocket. And they made it like 2 seconds prior to the vehicle exploding. And in the bottom right-hand corner, you can see the interior of the core module. Actually, you can see a huge collection of the videotapes. I believe both documenting what was going on the station and some entertaining ones as well. So besides of Mir NASA, another program was initiated which was called Mir Shuttle. So, and they actually were working in combination because Taggart came on board Soyuz, but he was replaced by Shannon Lucid, who was brought up on Space Shuttle, along with some useful provisions for the cosmonauts and for her as well. And the subsequent rotation of those NASA crew members was performed by Shuttle. And this picture is not actually a computer rendering. This is a real life photo taken by the Soyuz crew, which undocked and which was supposed to photograph Shuttle Atlantis undocking from Mir. And actually Mir is in a pretty interesting configuration here with crystal module brought up front for the sake of providing sufficient distance between shuttle thrusters and Mir solar arrays to prevent them from being damaged and spot over with the plumes of the thrusters. And that would have made for a nice video and lots of photos, but at this particular moment, a mission control center discovered a computer failure on Mir, and the crew had to rush back to dock and put everything into the order. But the picture is kind of gorgeous. So to avoid moving crystal to this forward position, that orange docking compartment was later brought to the station by the next shuttle mission, and the mission was, and Mir flew in this cross-like configuration. And here you can see the crew members who flew Mir. who were involved in Mir NASA and Mir Shuttle. You can see Sergei Krikalev, top right-hand corner, and another cosmonaut, Vladimir Titov, who flew their missions on Space Shuttle as a part of that program. Speaking of reusable capabilities, I should mention Energia and Buran, built in Soviet Union for the sake that it was system slightly different from Space Shuttle. Unlike Space Shuttle, Buran was just a payload for Energia launch vehicle. From the engineering standpoint, everything was going well enough. So Energia flew twice and Buran flew once. But unfortunately, the development and testing of the system coincided with collapse of the Soviet Union. So making no interest to the new authorities of Russia. So the program actually came to nowhere. I mentioned Mir NASA and Mir Shuttle as the first phase for the International Space Station program, and ISS consists of 3 phases. Phase 1, just like preparation phase. So it didn't only involve flying US crew members on Mir and flying shuttles to Mir, it involved the development of the station. And the story here was that that station, which started being developed almost at the same time with shuttle in 1970s, kept evolving. At one point, it acquired the name Freedom. Some international partners like European Space Agency, Japan, and Canada were brought in, but the development was going slowly enough. So at a certain point, some really wise people in NASA decided that it can't go that slowly anymore because it creates political problems for the agency and for the program. So at the same time, some drastic changes took place in politics on the other side of the world, and the idea popped up to invite Russia, and in particular Russian Space Agency, into this program and call it International Space Station, and the agreement was signed in 1993. So ISS operates under the International Intergovernmental Agreement, so and all the parties under that agreement performed their roles. So phase 1 was integration and testing, Mir NASA, Mir Shuttle. Phase 2 was construction, and phase 3 is what we are living through now, that's operation. So I was lucky enough to catch phase 1 in terms of engineering meetings, in terms of I slightly touched upon Mir NASA in terms of like supporting astronauts who were coming back to Mir in Star City, like Dave Wolf, for example. The development phase was extremely interesting because 2 engineering schools were to learn to work together. And believe it or not, inches, miles were widely used by the US engineers in 1997 when I joined the program. So there was a lot of challenges putting the station together, integrating various systems, various pieces of equipment which has already been designed by that point, and that they needed to be put together. So, but it worked. We can see the station in the sky now. This is how it was supposed to look. Unfortunately, it didn't work. It doesn't have all the modules which were outlined in this original configuration of 1998, but this is still quite impressive and quite sophisticated. You can see all the individual components a station is built of. And like if you take that US segment truss as a separation line on this chart, in the top left-hand corner, you can see Russian segment, you can see Zvezda service module, the Zvezda service module, Zarya functional and cargo module, Nauka multiple-purpose laboratory module, and two small modules called MRM1 and MRM2. Bottom right-hand corner, US segment, which has got truss, which has got a lab module, 3 node modules, Columbus orbital facility of European Space Agency, and Japanese experimental module. Plus Canadian robotics system, which actually contributed quite a lot to the station assembly in combination with space shuttle. So here are the specifications. No comments, it's quite impressive. Here is ISS, still with space shuttle, while shuttle was operational, and the reason why I'm giving this photo, that it's got quite a lot of vehicles docked to the station. You can see space shuttle, you can see Soyuz, Progress, and you can see European ATV cargo transportation system. So neither ATV nor space shuttle are operational these days, but we've got Nauka module seen here in the bottom. So this is the current configuration of the station, which, as we talked earlier today, currently is believed to fly till 2028. Out of the, I kind of missed the mouse here, but I'll try using my finger. Nope. Just a second. Okay. You can see a couple of interesting things. You can see that spherical module right to the left from the right solar to the right pack of radiators. So this is an inflatable module called BEAM. That's the first inflatable structure used on board the space station. And the story is that in early 2000s, Johnson Space Center developed that structure. Then the government basically killed it for the financing reason. And it was sold for a symbolic price to a private company called Bigelow Aerospace. And Bigelow designed this experimental module, which is inflatable, which is attached to the station. It's not used as a habitable module, mostly closed, but the crew occasionally opens it and checks it. So quite an interesting way to build the modules for the space station. And my time is running up. I would like to conclude. Questions? So what is one question I expected from that Salyut station? Sure. Okay, let's forget it.
So where is the Almaz with number 3?
Aha! So it was noticed. So that table was missing Salyut 3 and Salyut 5. And Salyut 5, Salyut 3 and Salyut 5 are essentially different stations built by the different group of designers, Vladimir Chalamet and his design bureau. And these were used for the Ministry of Defense purposes as the manned remote sensing facilities. I will come closer.
Yes. I have a question about current project in Russia, especially in propulsion. I want to know, does Russia have some project and plan to use green propulsion like methane and that Elon Musk try to use actually launcher or maybe nitros and some light hydrocarbon like ethane and methane for thruster in satellite. I think the method of design in Russian propulsion is for the some elder.
Well, so the short answer is yes, we are currently to go to employ energy Russian to go to methane oxygen engine for launch people. As far as I know, so that's what was published. No details.
Yeah.
So as for the rest, I'm sure about the propulsion systems itself, but as for the issue, because methane is a new program.
About nitros.
So we can see this ICCA. This the method of the parts belongs to the budget of the companies. For example, Roskosmos has their own 4 packs. Am I right? This initially developed
Four modules.
4 modules. Yeah. Also,
So 2 questions. The first question was about the developments in propulsion systems in Russia, and in particular about the methane and oxygen engines. And my answer was yes. NPO Energomash is working on one of those designs for Phoenix launch vehicle. The other question was how ISS operates in terms of assets, contributions, and all that sort of thing. So indeed, I would say the final asset, which is the number of the crew members on board, is determined based on the contributions of every single country. They are not equal. For example, Canada did contribute the robotic system, and occasionally they are getting a seat to fly their astronaut to the station. European Space Agency in pretty much the same way. They've got the module, they can fly their crew members. Japanese in the same way. In terms of US and Russia, it's a little bit more complicated because there is more factors in this game for Russia and for the US. That includes transportation, because, for example, for a very long time, so we are kind of even from the transportation standpoint because we are exchanging the flights. So NASA takes our cosmonauts on a single cosmonaut on every single flight, and we are taking US astronauts on every single Soyuz mission to the station. Also, what factors in is the resources on board the station. For example, US contributes quite a lot of electric power, and we provide the propulsion, because the reboost of the station and the active attitude control is performed by the Russian assets, such as Progress vehicle or the thrusters on the service module. For a very long time, it was like electricity in exchange for the life support, because Russian segment was a sort of the life support for the rest of the station while the station was being built. And it's kind of 50-50 right now because the US has got their own independent life support system. So essentially, it's not like everyone putting an equal share into the same pot, but rather contributing something critical and receiving based on the contribution. And I think Victoria is looking at me.
Can I have another question? Currently, what is the end dream of the space industry in Russia?
Well, I can't really tell you about the dreams of Russian industry. I do not represent the industry, but I believe that the dream would definitely not be different from the others. To fly to the moon, to fly to Mars, and I believe that might be a dream of everyone who is more or less caring about the space flight. Because as a human, as a biological species, we tend to expand on the area of our habitation. And we've got the Earth, and somehow I believe that strive to go higher is built into us, and it's to some extent it's easier going higher than going below. So I believe we'll be shooting for the lunar base. We'll be shooting for mission to Mars, which is kind of difficult right now from even the technical standpoint, but I believe one day we'll accomplish it. Thank you. And потом подойдешь ко мне, я тебе отвечу тогда на вопрос. Да. And I believe this should conclude the lecture. Thank you very much for your attention. Thank you very much for your questions. Enjoy the dinner and then enjoy the presentation of Mr. Rabi. Thank you.